Okay, good afternoon. So today we will try to have a few things on the limits and fits, and there what we will do is we will primarily solve a few problems, and then we'll also talk about how do you have tolerances on the gauges if needed, right? So that's what we propose for today. Okay. So this is where we ended primarily on the grades of tolerances. We are talking about what are the tolerance grades, right? So when you talk about things, there are, any limit will have one letter thing like A, B, C, and then after that there will be a digit which will be 1, 2, 3, 4. So this basically defines the fundamental deviation. So it will be P6, G7, H8 like that. So there will be a combination like P6, G7 means P6 shaft, G7 G7 is the P6 is the hole, G7 is the shaft, and this is the combination which we are using, and then this would have some sort of a fit which we will decide how do we get to that, and the diameter would be 10 mm or 20 mm. It can be any diameter. So basically P6 G7 10 mm diameter, P6 G7 20 mm diameter. So this is how you specify what kind of fit you want, and then you can basically check how it pans out to be. So typically, I think there are two things, right? The first one is letter thing, which is a fundamental deviation. Fundamental deviation. And this 1, 2, 3, 4, the second thing, which is a letter, which is a digit, that actually signifies the grade of tolerance. The grade of tolerance. And this grade of tolerance basically means 0, 1 to 1 to 4 is for gauges, plug gauges, measuring instruments, where you require very tight tolerances. Then 5 to 7 is for precision engineering applications. Then 8 to 11 is general engineering. 12 to 14 sheet metal, where you are trying to have higher tolerances. And then 15 to 16 is when you are doing cutting, casting, very coarse applications. So that's how you basically have this grade of tolerance. The lower the grade, the more stringent is the tolerance requirement. Okay. So this is what I wanted to give you some feel for what these grades of tolerances mean. Now, one of the things is this grade of tolerance is governed by something called standard tolerance unit. This is a very important concept. And here what happens is, for every D, this D is actually the geometric mean of the upper and lower diameters in which the particular diameter lies. So there's a table which I will show you. This I showed last time also. So if it is 5, it lies between 3 and 6. So for 5, it will be root over 3 by 3 times 6, which is 4.24. So for a 5 mm diameter, we actually use only 4.24 because that's what you use. If it is 6, if it is 10, then you use root over 5 times 10. Because it's up to including 10 is in root over 5 by 10. So root over 50, whatever that number turns out to be. Okay. So that's how you decide your D. Now, based on that D, there is a standard tolerance unit. So this standard tolerance unit is different for different diameters, right? That's the concept which you have to understand. So I is equal to 4.5 cubed root of D plus 0.001 D. So basically this I will change for, say, if I have 5 millimeter size, this I will turn out to be, if you do the math for 5 millimeter, if you do the math, the I will turn out to be roughly 0.723. But same thing, if you plug So 5 will be, you have to put D is equal to 4.24 here. And if you do the math, you'll get 0.723 microns. And if my D is say 20 millimeters, D is 20 millimeter, this will lie into 18 and 30. So basically D will be root over 18 times 30, which turns out to be actually 18 to 30, which would be, oh, there is 18 to 24. There are two zones here. So you have to use 18 to 24, 24 to 30. They are two different things. So if you are 20 millimeters, you have to do 18 times 24. So there's a step here. So you have to use 18 into 24 here. And this will turn out to be roughly 1.25 microns. So standard tolerance unit. So D you have to put here in millimeters. D is in millimeters, and what comes out of this equation is actually in microns. Any questions? You get what a standard tolerance unit is? Any ideas of what a standard tolerance unit means? Do you have any questions about it? Do you feel that this standard tolerance unit, what does it mean? It basically means that this is a metric which is a function of your D. So even if I say same, say I say IT6 or so IT6 for 3 mm will be different for 30 mm. The I will be different for both. And this is important because your tolerances should always be the function of your dimension. You cannot have tolerances independent of dimension. You cannot put, so if I have a 10 mm thing, my tolerances should take into account the actual size. And that's what exactly this thing does. Okay. So that's thing. So there is something which, so the first task what you have to do in any determination of any fit is you find out first this D, the geometric mean of the range in which it lies. That's the first task. Then the second thing what you will do would be you would try to find out what will be the standard tolerance unit, which is I. And then what happens is, if you see, this is the D. So basically for every grade, IT01 is point. So IT01 is 0.3 plus 0.008D. Okay. IT0 is 0.5 plus 0.1D. And this is 0. Sorry about that. This is actually acting up a little bit. And this is 0.8 plus 0.02D here. And IT2 to 4 are basically geometrically between IT1 and IT5. So basically 2 to 4 are between 1 to 5. So these are all these things which you'll have to see in the standard. These are there in ISO standards and IS standards also. And IT6 is 10i, IT7 is 16i, IT8 is 25i, right? And IT9 is 40i, 64i. So that's how these numbers are. These basically represent what will be the size of this tolerance band. So if this is my zero line, my fundamental deviation will be something like this, and this would be this grade of tolerance will give me what will be this dimension, what will be the size of the tolerance, or what will be the tolerance in some sense. So tolerance is defined by this grade. So IT6 will be 10i, IT7 will be 16i. So that's what basically it means. Okay. And then The fundamental deviation is something like this. You saw the picture first, right? The picture looks something like this. This is how it looks. For shaft, it is like this. For shaft, what happens is, it is till H, it is above the zero line. Till H, it is above the zero line, and after H, it is below the zero line. So basically, if it is H and lower than H, then it will be a clearance fit. See, so there is a larger hole and a smaller shaft, which means large clearances would be there. So you can look at it. So basically, if you see, these are the formula. A says minus 3.5D. Right? D for D greater than 120. For D less than 1 equal to 120, it's minus 265 plus 1.3D. And this is D is again in millimeters, and this dimension is in microns. So upper deviation ES is in microns. This is for shaft, and for the hole it is exactly symmetric, right? So for hole it will be capital EI and it will be positive. For shaft it is ES and negative. So EI basically means your ES is your upper deviation and EI is the lower deviation. So EI is the lower deviation of the hole and ES is the upper deviation of the shaft. And these are the formulae. So there are different formulas, 140, 0.85D, very large clearances you would see here, right? And CD is, take the, so if it is C, it's minus 5.2, 0.2. If you see E11, D 0.41, F is 5.5041, G is minus 2.50, 0.34, and H, it becomes 0. And then you would see the deviation flips. Now EI is the fundamental deviation, and at H is equal to 0, and everything else below H is now positive. So you go up the zero line. So you have here you have larger shafts. The shaft dimensions increase, so it's higher than 0. So its lower deviation is above the zero line. Okay. So this is what it basically means, these numbers. And you look at the formula. And there are a lot of exceptions here. If you look at it, for N, ES is equal to 0 for grade 9 or coarser. And if you see P to ZC for size 3 millimeter and above, you have different formula. So what you do is you don't use symmetry, but you use ES IT N minus 1. So if it is P, then I'll have to go. So if you go ahead and see, it is basically, if you go and see P for shaft, what do you see P for shaft? P for shaft is IT7 plus 025. But for hole, you know what will happen? It is IT6, because it says for, read this, special rule, lower deviation, you have the shaft of the same letter symbol, but one grade finer and of opposite side increased by the difference between the tolerances of the two grades in question. So this is EIIT minus N, ES plus ITN. And EIITN is ES ITN minus 1. So basically what happens is, whatever you are given, your shaft will be one grade lower. Oh, sorry, your hole, this is hole. Your hole is one grade lower. Okay. So that is what you have to see here. For P, there's a special rule. So basically for all conditions, for all deviation, this is for capital P. For all deviations, see the rule here. The rule says holes are identical with the shaft limits symbol on the other side of the zero line. That's it. So this is very symmetric, but these are the exceptions. These three are the exceptions. So as you do more problems, you will get more familiar with it. Okay. We'll do some of these cases so you will have a better understanding of what I'm talking about. Okay. And then if you see, so that was for till 500. All this was till 500 millimeters. If your shaft is more than 500 millimeters, then you go ahead and you have these formulae. So these go from 500 millimeters to 3 meters. So these are for large shafts, for large dimensions. For large shafts, you have to use this chart. Okay. All these are then the standards. I'll actually, if you want, I can give you the standards as well. Okay. And the selection of holes. So which holes you can select? So these are the letter grades for 0 and 01 grade. You can have only H and JS. But as you grow coarser and coarser grades, right, these are very tight. 1, this, 2, these are very tight tolerances. So there are certain kinds of fits which are allowed. But as you grow in your grades, this tolerance band becomes larger and larger. You have more number of combinations possible of shafts and holes. Okay, so you see, so as you have coarser and coarser grades, meaning your tolerances becomes larger and larger, tolerance band becomes bigger and bigger. You would see that you have lot more combinations of shafts which are possible. And same, like you can choose all these. So these are the shafts which are available for you. Okay. And if you really want to understand what kind of grades are used in what applications, so basically A, B, C, and 11, which is a very coarse grade, they are very large clearances. So you don't really use it. So D, 8, 9, 10 will be loose running in loose pulleys, right? E, 7, 8, and 9 are loose clearance, electric motor, bearings, heavily loaded bearings. This F7, F6, 7, 8. So F6, 7, 8 basically would mean, let me just write what F means. Let's go and see what F means. So F is basically the shaft has some zero line will be here, and it is negative 5 minus 5.5. So this will be my upper deviation. Sorry. So the upper deviation of the tolerance band, this would be, if you go ahead and look at it, it will be minus 5.5D raised to 0.41. So this will be the top line, and depending upon your tolerance band, which is in this case, we said it is basically G6, right? Any questions? Any questions you guys have? Okay. So basically, if you see what we're talking about is G6, and 6 is nothing but, if you go see, 6 should be roughly 10i or something. Let me go and see. 6 is 10i. So basically, if you go, this would be, this dimension is this 0.5D41, and this is 10i. This band which is there from the maximum diameter to minimum diameter is 10i. So this will be G6. We'll actually use, we'll show you more when we get there. So basically G5 and 6 is precision running. H5 and 11 for extreme clearance. Now, if I want to have preferred clearance fits, these are the fits. This is H11, C11, H9, D9, H at F7, H7, G6. This is a guide fit. This will be snug relatively. G7, H6, C11, H11, F. So these are the clearance fits which you should use. These are recommended. And then in transition fits, if you see, then there's GS567, K567, M567, N567, and H7, K6, H7, N6, K7, H6. And these are for accurate location, couplings, spigots, gears, precision where there is a lot of vibration. So if there is vibration, you cannot have a lot of clearances, right? You have to take care of that. Like these are basically for lubricated bearings, lightly loaded shafts, and sprockets. So there is these are for non-running parts, H5 and 11, right? And these are for running parts. If you have lubricated bearings, pumps, small motors, these are for lightly loaded shafts. So you have to pick what application it is and identify which. So based on this handbooks, you can choose which combination I have to use. So these are all given that for accurate location, couplings, gears, precision joints, where forced assembly is required. So these are the combinations which you have: H7, K6, H7, N6, H7, K7, H6, and N7, H6. Okay. And then if you see interference, this was transition fit. These are the preferred transition fit. The first one was clearance, second one was transition. The third one are interference. When you have bushes, when you have keys, when you have valve seatings and permanent assemblies, then you have very high. So H7 P6 is a press fit. Then S7 U6, P7 H6, S7 H6, U7 H6. These are the preferred interference fits. There will be a physical interference, right? Then you will have to heat it up and put it, or apply a lot of force to get in. Okay. And in some cases, these are high degree of interference. So then you will have to probably use some sort of a heating, and then so basically these would be shrink fit kind of a things. So this is something called an ANSI standards. So I'm using ANSI B 4.2. This is what is recommended from American National Standards Institute. They actually tell you what applications. So clearance, they say used for these applications. For loose running, let me just blow it up if possible. So basically, this is for C11, H11. Sorry, I didn't expect this to happen. Okay, so basically H, if you see, these are so there are hole bases and shaft bases. So there is H11, C11, and C11 and H11, and these are. So these are for loose running. So this combination, sorry, it looks like it will not let me write if I blow it up. So I'll not blow it up. So H11, C11 and C11, H11, if you see, this is the hole basis, this is the shaft basis. Shaft basis means the shaft is the standard and hole is this thing. So basically, if you see, this is for loose running, this combination. This is for loose running. And H9, D9, D9, H9 are for free running. So these are clearance fits for free running. Sorry. It's like there is. Just 1 second. Let me see what the problem here is. Sorry about this. So basically, then this is free running fit. This is closed running fit. H8 F7 F8 H7. H7 G6 is a sliding fit. So it's not intended to run freely, but to move and turn freely and locate. And this is locational clearance fit. H7 and H6. So what it does is provides snug fit for stationary parts, not for rotating parts, right? Then there is transition fit. So the transition fit is H7 K6 for accurate location and a compromise between clearance and interference. And then locational transition for where greater interference is possible. So H7 N6, N7 H6. Now after this, these are interference fits. H7 P6, P7 H6. So these are for parts which are rigidly and alignment with prime accuracy, right? So you need very good alignment, and maybe it's a rotating part also. For accuracy, steel parts, shrink fits on light sections, and then force fit, which can be highly stressed, or shrink fits. So these H7 U6, U7 H6, these are shrink fits. So these will be a sleeve on a shaft which is permanent, or in some cases some bearings which will be permanent. So these will be the fits which you can choose. So there are these kind of guidelines which one to choose. Okay. So this is what I am discussing. So I've given you some of those combinations here which you can use. And what I will do is I'll take two problems. In one, there is H7 G6. So H7 is the basically hole, and G6 is the shaft. So you see here, there's one combination which I will choose. The other combination which I will choose will be H6 and P7. This combination. Two combinations I will choose, and we'll solve these problems. And this is H6 P7 combination. So let's do two problems. We'll go step by step. The first one is I have a diameter 6 of H7 G6. Right, let's go ahead and do this. I have a 6 mm nominal dia, and I want capital H7 G6. This is the fit. This is the pair. I have to find out what kind of fit it is. What kind of fit it is. How do I go ahead and do it? What will be the first task? Can somebody tell me what will be the first task here now? What do I do first? Let me know, just type it out, whatever it is. What do you think I should do? The first task, what I should do? Yes, the first thing should be calculate D and calculate I. So second should be calculate I. You're very correct. So first what I do is I calculate D. So D, if you remember that 6 lies between what? 5 and 10, right? 6 lies between 5. Actually 6 lies into, let me go ahead and see that. I did not look at it then. What are the diametral steps? Sorry, what happened here? And so, what was happening? Okay. So 6 mm lies into 3 and 6. Sorry, my mistake. So it lies between 6 and 10. Actually, this is, oh, sorry. This is up to and including, right? So 3 and 6. So it should lie between 3 and 6 because it in 3 and 6 is up and including. So 6 is included here and it is from 7 to 10 will be in the other one. Right. So let's go ahead and do this. So I have 6 millimeter. Sorry. I have 6 millimeter G7H6. Right. 6 lies between 3 and 6. So basically it's 3 times 6 geometry mean of 3 and 6, which is 4.24. Now I have this is the first thing I calculate. The second thing is then I calculate I. So I is nothing but 0.45 cubed root of D, which is 4.24 in this case, plus 0.001 D. If you do this, you will actually get that as roughly standard tolerance unit would come out to be standard tolerance unit comes out to be 0.732 microns. So this is plugged into millimeters. This is millimeters. This is plugged into millimeter and you get in microns. So this you have to always remember. This equation is not a dimensionally consistent equation. This is not a dimensionally consistent equation. Not dimensionally consistent. Right. So you have these two equations. So now let me draw the zero line here. So I will draw the zero line here. This is my zero line for reference. Now, if I do G7, let's do for G7. Right. So I have to find out two things here for G. For G, I have to find fundamental deviation. And for 7, for the shaft, for the G7 shaft, I am doing this. Right. And 7 is the grade. Right. So let's go and see what does IT7 mean. So IT7, if you go ahead. Sorry, why is it behaving like this?
So,
yeah.
Why is that I equation dimensionally inconsistent?
Because these are empirical equations. These have been fit. So a lot of data is there, right? And this data has to be valid for a lot of conditions. Some same equations are valid from 1 millimeter to 500 millimeter. So what people do is people try to figure out what equations would fit. So these are not physics-based things. These are just data fitment. Okay. So data has been fit in a way that if you plug in D, you get those tolerances in microns. You get me?
But if we if it is ever possible to understand the physics behind it, it may be possible that the dimension is.
First thing is it's not a physics thing. They have data, right? They know it's an experiential thing that for this shaft I need this much tolerances, and the tolerances will always be a function of two things: your size, right? And you need standards. You cannot have standards for every size, can you? You cannot have different standards for different sizes, right? 10 mm ke liye you have other standards, 50 mm like standard. You cannot have that kind of a thing. You may have a lookup table, right? You can create a lookup table for that, but that will be very cumbersome. So it's like a lookup table, but these lookup tables have a formula for it. So there is a formula which you can apply. So people have done a lot of work to come with these equations, right? Because these equations actually fit for such a wide range of shafts. From imagine 1 millimeter shaft, right? Which is almost like a big fat needle, to a 500 mm shaft with half a meter shaft, and you're using the same formula for that, right?
Right.
So if you don't appreciate how they would have been able to evolve equations which are valid for such a wide range, It's pretty smart how they were able to do it. So they actually use a lot of statistics to get those equations, which are best fit, which actually fit the tolerances required. So people would have made the lookup tables, and based on that, they developed equations which will fit that very precisely. So it's nothing but a very good data fitment.
Even if it is data fitment and all of that is experimental, isn't it possible that the dimension which is missing from the when we take cube root or some different power, fractional power, the dimension is hidden inside the constant?
These things, these units are reason. There is a reason why they have used millimeters and microns. Tolerances are never measured in. So these are the units which engineers use. Tolerances are always measured in microns, and diameter is always measured in millimeters. So you'd think that they have done it dimensionally inconsistent. It's not dimensionally inconsistent. For an engineer, this makes more sense, because diameter is never measured in microns, and tolerances are not measured in millimeters. Tolerances will be 5 micron. So in the shop floor, nobody will say 0.005 thing. Actually, if you see in US, they still do. They actually use thous. So they use inches and thous. So thou basically means 1,000th of an inch. So they will say 2 thou. So 2 thou tolerance is there. 1 thou tolerance is 1 by 1,000 is the tolerance, and 2 is inches. So a counterpart in SI units is that your shafts is in millimeters and your tolerances are in microns. So it's not that they have made a mistake here. It's by design, because your tolerances are always measured in microns and your shafts are always measured in millimeters. If till a meter or so. After that, people will use not use 3 meters. They will use, but till half a meter or something, you would use still 500 mm. So that's the standard notation which is being used. Okay. There is a good reason for it, because those are the used dimensions for. So tolerances are measured in microns, the sizes are measured in millimeters. That's why they have done it. So that's what people use. It's not a mistake. It's what the popular usage.
Okay.
Okay. So basically, let me go ahead and do this. Where were we? So we were here, right? So we have to find G. Let's go to G. Let's go to G. So G is minus 2.5, 0.34. So minus basically means lower than the 0 line. Minus 2.5. So G is nothing. So if I have G is nothing but minus 2.5 D raised to 0.34. Go ahead and do this. So minus 2.5 D is 4.24 and this is raised to 0.34. If you do the fundamental deviation, which is in this case ES. So ES is equal to, so top line would be equal to, this dimension would be this. Which, can somebody do this for me? 4.24 raised to 0.34. This turns out to be, if you go ahead and do it, this turns out to be minus 4 micron. So this is minus 4 microns. Now, IT7, the extent or the band of IT7, if you go ahead and see, IT7 is nothing but 10i. Oh, actually, no, G6. G6 is there, right? I'm saying G7, no, it's G6. G6 and H7. Oh, it's G6, H7, yeah. It's other way around. G6 and H7, I'm sorry. And IT6 is 10i. This is actually an old PowerPoint, so that's why I think it's acting up. IT6 is equal to 10I. So 10I will be, this is I is 7 point, this will be 7.32. So this is 4 microns, and this will be 7 microns. 7 microns. So this is the, if you see, if say this is the baseline, so this would be, this from here to here is 6 millimeters. So what is D min? D min is what? 6 minus 4 minus 7. Actually, let me just put the right thing here. 6 minus 0.004 minus 0.0073. So this will be the minimum diameter. What will be the maximum diameter? D max will be 6 minus 0.004. This is the shaft diameter. Now, how do we find H7? What is H? You remember? You guys remember what H is? I've been telling you H is what? Where the H hole will lie? Capital H, where will it lie? Anybody? FD is fundamental 0. Basically means fundamental deviation for a hole is capital EI. So capital EI is equal to 0. Capital EI is equal to 0. Capital EI is equal to 0. Which basically means it will just start right from here. And then, so this is my EI. So my EI will be somewhere here only. This is my EI. Now the band for IT7 is 16I. If you go and see, I'll just show you there. IT7 is 16I. Okay. So 16 into 0.732 is what? 16 into point. So this will be the thickness would be this D 16 into 0.732 is 12 microns. So this dimension right here is 12 microns. Right. So capital D min will be 6 and D max will be 6 plus 0.012. 6.012. Right. So this is the maximum minimum difference. This is the tolerance on the hole. This is the tolerance of the shaft. So this is hole. This is shaft. So what kind of fit is this? What kind of fit is this? Any ideas? What kind of fit will this be? The maximum diameter of shaft is smaller than the minimum diameter of the hole. So in any combination, so I can, yeah, very good. It is a clearance fit, and in most cases, so I can make my shaft for this. I can make my shaft here also, this size also, this size also, this size also, this size also. As long as I am between this D min and D max. So as long I have this 7 micron tolerance, I have to make my shaft between these two limits. I have to make my hole between these two limits. So I have to make my hole between 6 microns and 6 micron and 12 micron, 6.012 micron. So this should be this is my limit on the hole, and this is my limit on the shaft. If my shaft is, if I make a shaft here or make my shaft here, I reject. Then this is not this G7H6 combination. Okay. Or if I make my hole here or here, I reject the hole. Right. This is how I test it. Now I'll come to how do you test it. I'll come in a little bit. Let me do another problem, and then I will ask you how do you test that. Right? How do I measure those holes? How do I measure those shafts? We'll come to that. Before I do that, you have any questions here? Any confusion or any questions here? So I can go over it again before we go to the next thing. You have any questions here? It's very clear, right? How do you identify a combination of preferred shaft and hole combinations? This is how you do it. The first task is you find out the D, then you find out the standard tolerance unit, then you find out the fundamental deviation, then you find out that what is it called, that tolerance band, and then plot it to see where it is with respect to zero line. Zero line. The moment you'll plot it, you'll get to see whether it is interfering. So right now my hole is in all cases bigger. So if my plot looks something like this, means it is transition. Some cases it will go, some cases it won't go. Right? If this is my hole and this is my shaft. Okay. If you have any questions, ask me. None? Okay. If none, then I'll move to another one. So this is what we plotted. This is how it will look. This is the zero line. This is the zero line. Okay. And this is the fit. So the maximum size of the hole. So we can know the maximum size and the minimum size. So this will always be the, so there will be a 4 micron clearance always between the two. Okay. In the worst condition. In the best condition, what will be the clearance? In the best condition, the clearance will be 12 microns plus 4 microns plus 8 microns. So there will be 12, 8, 20, 24 microns. So maximum will be 24 micron clearance, minimum will be 4 micron clearance. Okay. So let's do this. 520 P7H6. So I have 520, 20 diameter P7H6 combination. Let's go ahead and do it. So my zero line is somewhere here. Now first thing is I have to find D. So D, let me see what D is. D lies between 8 to 24, because if you see here, this 18 to 30 has two steps. The first one goes from 18 to 24, the second one goes from 24 to 30. So I'll have to use 18 to 24. The step I'll have to use 18 to 24. Let's do 18 to 24. So this will be root over 18 by 24, which is equal to, it is 20.78. If you go and do ahead the math, this will be 20.78. Now I have to find out the standard tolerance unit. I is equal to 0.45 cubed root of B plus 0.001 D. Now if you do this, you will get, this time the I will be slightly larger, which will be 1.258. So I can say 1.26 roughly. 1.26 microns. Right. Now I have to find out the fundamental deviation for P. Right? Fundamental deviation for P. What is the fundamental deviation for P? Let me go and look at it. Let's look at the table. For P for shaft is IT7 plus 0 to 5 microns. And IT7, if you remember, it is 16I if you go and look at IT7 table. But there is a caveat here. It says from P to ZC for size above 3 millimeter, there is exception which says that EI minus ITN is equal to ES ITN minus 1. So basically what I have to do is I have to use whatever the grades are there, I have to reduce one grade. So it will be IT6 plus 0 to 5 for shaft. You have to read this and then you see this is a special rule which you will have to follow here. So go ahead. So this is so basically fundamental deviation of P shaft is IT7 0 to 5 we saw in the table. But now for P7 hole it will be IT6 plus 0 to 5. It will be IT6 plus 0 to 5. And IT6 is 10I, we have just shown that. So basically it can be two things. Now my fundamental deviation has a range now. My fundamental deviation now, P hole basically means IT6 plus 0 to 5 microns. 0 to 5 microns. So IT6 is nothing but 10I, so it will be 12.6. So it will be 12.6 plus 0 or 12.6 plus 5. So either it will be 17.6 or 12.6. So I can do, let me do two cases. I'll take the extreme case, right? So in one case I take 0. So in one case the fundamental deviation would be, if I take the lower limit, my fundamental deviation will be 12.6. 12.6. In other case, if I take 5, my fundamental deviation, and this is only for the whole, right? 17.6. So either 12.6 or 17.6. This is it is P, right? So what is this? Is it capital EI or capital ES? What is that? What will this be? Can somebody answer me? The band will come down or go up? What is this? Is this ES or EI? So this is ES or EI. Which one is this? What is the fundamental deviation? It has to be exactly opposite of, so let me go ahead and see here. Here it is EI. So for shaft it should be ES. You see, this fundamental deviation is EI. So H, basically P is below the 0 line, right? For whole, if you see, it is basically, if you see EI, it is positive, right? So basically it is somewhere here. So for shaft, what will happen is, it will be for shaft it will be other way around, right? It will be ES. This will be the fundamental deviation of this, right? So it will be a smaller hole. So if I have to do this, let me go ahead. So ES will be negative. So this, where should this come now? This should come here, right? Typically, my hole till H is above and this is below. So this should be, this is ES, right? This is ES, which is the upper deviation of the hole. Oh. Okay. So this is ES. This is ES, and this is one side it is 12.6, the other side it is 17.6. It is 17.6 microns. Right? Now, what is the? It is 7, right? IT 7 is 16I. 16I is how much? 21 microns. Right? So this is 21 microns. This will also be 21 microns. Both will be 21 microns. 21 microns and 21 microns. Right? Now, where will the hole lie? H6. H is what? You remember H is what? 0, right? H has 0 fundamental deviation. Now, H will lie. So H is 0, and what is that? Is it EI or ES for H? Can somebody type it? What is there for shaft H? Okay. Any answers? So will it be below the 0 line or above the 0 line? Where will it be? Below or above? How does shaft go? Till H? So if you go ahead and see shaft's limits, let me just go ahead and show you again. Where is the table? Yeah. So H is 0, but it is the upper deviation. Right? ES. So shaft is smaller than the 0 line till H, and then it flips. So we have to have, so this is the ES of that. So both have ES only. You see that. This is the thing. Both have ES only. So here also it is ES, and here also it is ES. For shaft, what will that be? 0, and then it is 6 is 10I. IT6 is 10I. IT6 is equal to 10I. So I know 0, so this will be 10 microns. This will be 12.6 microns. Exactly this. This is 12.6 microns. What kind of fit is this now? Tell me. What kind of fit is this? So this is my shaft. This is my shaft. This is my shaft, and these two are the holes. Extreme conditions. So my shaft is always bigger. The lowest dimension of my shaft is always bigger than the hole. Right? So if you see, extreme condition will be what for this? So maximum interference will be, right? Maximum interference, if you want, will be this, which is which is 17.6 plus 21. This is the maximum interference, right? So by shaft can be this big, hole. So maximum dimension of shaft is this, minimum dimension of hole is this, right? So shaft is much larger than the hole. So this is the maximum interference. This is the maximum interference. And here, what will be the minimum interference? So what is this fit? This fit is perfect interference, right? If I close this, for now you forget about this. For now you forget about this. What kind of interference is this? What kind of interference is this? What kind of fit is this? Sorry, this is interference. This is interference in which the maximum is 21 plus 17.6, right? 21 plus 17.6, 39, right? Maximum of 39 micron. And what will be the minimum in this condition? Minimum interference? Minimum interference, if you see, will be this, which is 17.6 by 5 microns. Minimum interference is 5 microns. Right? So if you see, so shaft maximum dimension of hole is this. Maximum clearance. So this is what you see, right? So basically your maximum dimension of the in the worst, so your minimum this is the maximum hole, and this is the minimum shaft. So minimum shaft is bigger than the maximum hole, right? Agreed? So this will always be what? What kind of fit is this? Somebody? Complete interference, right? Because your maximum, if you see here, this is your shaft, and this is your hole. So your hole in any condition. So your biggest hole is smaller than the smallest shaft. So it will always interfere. Now let me take this. So I actually take this off now for time being, and I make a ES here. Right. What kind of fit is this? If I take the lowest boundary, what kind of fit is this? Now tell me. Anybody? What kind of fit is this? What did you call this? Will you call this interference, or what will you call this fit? That's my question. It's interference in all conditions, but if you are just flush, imagine I make the biggest hole and smallest shaft. In that case, what will happen? you can call this transition. In one case, it can be transition because then it will be exactly be the same. Right. So you can get close to transition in one condition. That's it. You just flush. But by and large, this is still interference. This entire thing will always be interference, except one condition where your ES and EI of shaft and ES of this merge, they are very close. They are same actually. So you can call this as a transition because there it will be, you can go. Now, I ask you one thing. I have this, I showed you these kind of things, right? Shafts. So let's say this is zero line, this is the, so let's say for the, it's a clearance thing, this is hole, this is shaft. And how do I measure these things? How do I measure a hole? If I have to make a gauge for measuring my dimensional accuracy, how do I go ahead and do it? Can somebody just make a guess? How do I do that? Anybody? You can either type in the chat box if you have any ideas. What do I do? Actually, it is there in the slide. Different sizes of shafts. Actually, what you do is you have a gauge which is called plug gauge. It's like a shaft, but it's a plug gauge. So plug gauge means it's a go gauge. It should go. So which one should go? How do you, what size will you make the go gauge? What size the go gauge should be ideally? If I have this hole, my go gauge should ideally be equal to this size, right? Should be equal to my D min, right? If it is D min, it should always go, right? So I'll make my hole. Ideally, the gauge should be D min. And the no go gauge, what kind of gauge will be no go gauge? So no go gauge. So if I have a hole, what size will be no go gauge? That will be, sorry, this will be D max. So if I should ideally make it the size of D max, ideally, I'm using these ideal. Any ideas why I'm using ideal? So ideally I should make D min and ideally I should make D max. If in a perfect world, if I were able to make it, I would make my gauge a go gauge of the size of D min, no go gauge for holes, no go gauge for D max. It's not ideal world, right? So there will be a tolerance on this, right? So now you tell me, if I have to make a gauge to have this is the tolerance on a hole. What kind of tolerances should I put? So I know that dimension should be D min, right? So this would mean, so D min will be zero line for my gauge, right? For my go gauge, zero line. What is the tolerance which I put on this? Where should I put? Should I put tolerance in this direction or in this direction? Let's say up, down. Who is the brave soul who will tell me where should I put the tolerance? Should I make my gauge slightly lower than D min or slightly higher than D min? Let me just put low and high. That will be good. Low or down, ठीक है? Everybody says down. Should we go down? Should we go down? If I go down means I make my gauge tolerance this, right? My gauge tolerance is this. So my gauge will be smaller than d min, right? My gauge can be smaller than d min. So these many defective pieces I'll capture, right? So actually I will measure holes which are defective, these many defective. Yes or no? If I go down, so if my gauge is something like this, if my gauge size is this, means my actual hole is smaller than my design, but still my gauge will say it's okay. So if this is the zero line, right? If this is the zero line and I make, so you're saying that I'll make my gauge tolerance here, this side. Is it correct? Should I do that? Yes, I like the answer. Yes, but if up, you will reject some acceptable pieces. So if I'm gauging, should I accept, if I'm gauging, what should be my thought process? Should I accept defective pieces or should I reject acceptable pieces? What is your opinion? What should be the thought process? If I'm gauging, right? If I'm very quality conscious, what should I do? Yes. So I would rather reject some pieces, make a very tight tolerances here, reject some pieces. So this will be the tolerance on my go gauge. On my no go gauge, again I will go the other way around. I'll come down. So in this case, I am rejecting some good pieces. In both cases, in both go and no go gauge, I'm rejecting some good pieces, but I'm not accepting any bad piece. Right? So that is true that I'm rejecting some acceptable pieces in both cases in go and no go gauge, but still I'm ensuring that I'm not getting a single faulty product out. Right? So that would be one way to gauge. If you want very accurate gauging, this is how you define the tolerances on your gauges. Now, can somebody tell me how do you design how would you measure a shaft? What will be a good way to measure a shaft? How would I measure a shaft? Any ideas? Hole like gauge. Shaft के लिए hole like gauge, which will be what? Any example? Have you guys seen chudi? Right. You can have a ring gauge. So hole like gauge basically means you're right. The shape is still a hole, but chudi is exactly a gauge, right? When you see the chudi wala actually knows what the size is, and then he slides the chudis right to the size for you, right? So you will have a ring gauge. So now again, same thing on the ring gauge, right? What would be the size of the ring gauge? Go gauge ring ka kaisa hona chahiye? Which one should go? Which dimension would the ring go gauge measure? D max or D min? D max or D min? Ideally, it should be what? If it's a go gauge, what should be the size? हाँ, छोटा वाला D use करो भाई. Correct. So D max. This should be D max, go gauge, and D min should be no go gauge. No go gauge. Now again, the tolerances you will do the same thing. If you want to ensure that there are no defective pieces, then you go eat up some good pieces. So you can basically reject some good pieces, but you don't accept one crappy piece. So that's how you set tolerances on the gauges. I'll give you a problem. When I give you the homework, I'll give you a problem for that. Okay. Any questions here? I think now I've covered whatever I had to cover. So basically, I'll just read it out. A combination of go and no go gauge will give you the exact dimensions, and plug gauge basically checks so the go gauge actually checks the maximum material condition, smallest hole or the largest shaft, right? And no go gauge basically ball gauge for minimum material and it tests maximum dimension. Okay. Okay. So now with this, I think gauging is over. So what I will do is I'll just stop here and we can have some small discussion. If you guys have any questions, anything about the projects you want to ask me, whatever your questions are, go ahead and ask those questions now. Okay, I will still have, I think, 5 more minutes we have for discussion. I think more than 5 or 10 odd minutes we have. Okay, so I'll stop here. You want to talk about this thing? I'm happy to talk about gauging or even tolerances. Or what we could do is we could talk about your projects if you have any questions. Any questions? None? Any questions about the projects also? None? Okay, I'll wait for a few more minutes. If you have any questions, feel free to ask me. If not, then you're free to go.